Have a look, please. All right, so I want to go through one quick example, and then I'm going to turn you loose on this assignment, the graphing rational functions assignment. Okay, so what do we do here? What's our strategy? What's one thing we can do? Okay, we could factor. Yeah, we could factor the top. What could we factor on the top? Okay, good. We could take out a negative x, leaving us x plus 1. Okay. And on the bottom, we've got x plus 4. Okay, so what's that tell us then? Something else. Yes, sir. Atticus. Okay, x cannot equal negative 4. And what is going on at negative 4? Let me. Okay, it is. How come? You're right. Tell us why, though. Say it again, Atticus. Okay, because negative 4 is a 0 of the denominator, but not the numerator, which makes it a vertical asymptote, right? Okay. All right, so we could add that to our graph down here. X equals negative 4. So we got a vertical asymptote. Any horizontal asymptotes? Yeah. No. Horizontal asymptotes. Do we get a horizontal asymptote? Huh. We don't get one. How come? No. We have a rule. You got to don't look at this one. You got to look at the original one. How can we look at that until? Okay, good. So we're looking at the ratio of the leading terms here, right? If we're looking at as x approaches the infinities, and what happens? Well, they, if I look at that, we get f of x equals negative x squared over x, which doesn't end up being a constant. We had kind of a rule, didn't we? We were just able to look at rational functions, and based on the degrees of the polynomial in the numerator and the polynomial in the denominator, that told us a lot about horizontal asymptotes. When do we get a horizontal asymptote at y equals 0? Under what conditions? What can you tell me about that? What would have to be true for the degrees of the numerator and denominator for us to get y equals 0 as a horizontal asymptote? What has to be true? Good. Okay, so the degree of the denominator would be greater than the degree of the numerator, right? That would give us a horizontal asymptote at y equals 0. Well, that's not true. When would we get a different horizontal asymptote other than 0? Right, like if we look back at a couple previous examples from last week, we said, let's see, we said, here's an example. No, there's not an example. There's an example where we got a horizontal asymptote at 5, y equals 5. How did we get that? Well, we get it. There's two ways we could do it, right? We could do it because if we look at the ratio of the leading terms, they simplify to y equals 5. That's one way to do it, right? The other way to do it would just be to say, well, look, the degrees are the same, 2 on the top and 2 on the bottom. Remember what our rule was for that. If the degrees of the polynomials are equal, then you get a horizontal asymptote at y equals the ratio of the leading coefficients. It's always going to work that way, right? So here we had a 5 over a 1 equals 5. That's our horizontal asymptote. Take your pick. That we're saying the same thing, right? When we look at the ratio of the leading terms and we take our limits, that's a little more sophisticated calculus way of saying it, right? You guys can do it that way, but we do have the simple rule, just compare the degrees. They're equal, so then we get the ratio of 5 over 1 Gives us y equals 5, right? Okay, now what was the case where we got no horizontal asymptote? What was true there? Yeah, the numerator is a higher degree polynomial than the denominator, right? And then we don't get any horizontal asymptotes. And that's what we've got going on with this last example. Yeah, look at that. See, we've got second degree numerator, first degree denominator, so no horizontal asymptote. Okay, but there was a unique situation where if the degree is exactly 1 greater than the degree of the denominator, even though we don't get a horizontal asymptote, we do get an asymptote that's useful. How did that work? Right, you guys remember this? We did this example, right? And what do we do here, right? We divide it out. If we simplified this quotient using long division, or in this case, we can just use synthetic division, we divided that out. What did we get? Well, we got our polynomial was equal to x plus 2 plus the remainder 4 over x minus 2, right? Remember this stuff? And now if we take our limit as x approaches plus or minus infinity, that orange fraction is going to go to 0, right? Because look at the orange fraction. That's a rational function where the denominator has a higher degree polynomial than the numerator. The numerator is degree 0, denominator is degree 1, right? So in the limit, that goes to 0, and we're just left with x plus 2. So that means we have the slant asymptote or oblique asymptote. Different books call it, one or the other. The slant asymptote y equals x plus 2, okay, which was useful to us because when we graphed this guy then, look, we had the vertical asymptote at x equals 2, and we had the slant asymptote at y equals x minus 2, and combined, that really helped us graph the function, didn't it, right? When we have those asymptotes, okay? So how about this one then? What are we going to do here? One higher degree in the top than the bottom, so what do? Synthetic division. Any kind of polynomial division, but we might as well do synthetic here, right? Okay, so if we do this synthetically, what numbers go across the top of my synthetic bracket? Okay. And what number goes out front? -4. We want the 0 of the denominator, right? And now we just bring the -1 down. -1 times -4 is 4, plus -1 is 3. I get a -12 plus 0 is -12. So what's that telling us then? That's telling us that this function, f of x, is equal to -x plus 3 plus my remainder of -12 over my original denominator, x plus 4, right? And if we take our limit as x approaches the infinities, what's going to happen here? What happens if we take the limit as x approaches plus or minus infinity? Yeah, look, that fraction right there is going to go to 0, right? Because the bottom is blowing up and the top is not. So the fraction gets small, right? Okay. That one goes to 0. So what's that tell us then? Well, we get a slant asymptote, right? We get the slant asymptote y equals -x plus 3. That's very helpful. Now we can graph -x plus 3 on our graph down here. -x plus 3 is just going to go like this. Right, and I've got those two asymptotes now. I maybe needed to make that graph a little bigger, didn't I? Let's do that. I don't think that's a big enough graph. There, that's better. Okay, so again, if we graph this guy, we had a slant asymptote at negative x plus 3. So negative x plus 3 is just a line with a y-intercept of 3 and a slope of negative 1. So there it is. And then we had a vertical asymptote at negative 4. So right there. Right? Everybody see that? Boy, it still doesn't leave me much room for that top graph, does it? So there's my asymptotes. What else? Do we have any x-intercepts? Where do the x-intercepts occur? Where the numerator is equal to 0, right? So what are the zeros of the top? X equals 0 and x equals negative 1. Those are unique zeros of the top, right? We know a fraction is 0 when the top is 0 and the bottom is not. So if we look at the zeros of these functions, or those factors up there, we get an x-intercept at 0, 0, and at negative 1, 0, right? Okay, we haven't talked about this yet, but when I built this assignment, there's some problems that ask you to do y-intercepts too, which is easy. Where does y-intercepts are always really easy to calculate. Where do y-intercepts occur? When x is 0, right? So we could just come up here and say, okay, well then f of 0, if I plug 0 in for x, I just get 0 times 1 over 4. Well, 0 divided by a number is 0, isn't it? So my y-intercept is also at 0, 0. That's both an x-intercept and a y-intercept. So I only get 1 point there, okay? But that should help us out quite a bit then. So if I plug these points in, negative 1, 0 is right there. 0, 0 is right there. Can anybody tell me what is this function doing here to the left or to the right of this vertical asymptote? Think about what this behavior's got to be, and you got to kind of just think in terms of a puzzle. There we go. It's got to stick to the asymptotes and go through both of those points. So doesn't that mean it's just doing this? Like that? Everybody see that? That's the only thing it can do. It's only got 2 x-intercepts, no more, and it's got to stick to those asymptotes. So that's the behavior. Okay? What's it going to do to the left of that vertical asymptote at x equals negative 4? How would we find out? Test point, absolutely. We'll plug in a test point, and what would be a good value to pick for our test point? Well, negative 2 I don't want to pick because that's not to the left of negative 4. Negative 5, how about? Yeah, if we plug in negative 5 into our function, well, what do we get? Again, if we just go up here and evaluate our function, f of negative 5, we want to use the factored form, don't we? Right? It's easy. It's much easier to plug stuff in. So if I plug negative 5 in, negative x is positive 5 times negative 5 plus 1 is negative 4 divided by negative 5 plus 4 is negative 1. Well, that gives me negative 20 over negative 1. What's that? 20. So if f of negative 5 is 20, look, I've got the ordered pair, negative 5, 20. Well, negative 5, 20 is way the heck up there somewhere, isn't it? Everybody see that? So what's this thing doing? Well, we can't even see it because it's off the graph, but it's doing something like that up there, where it's up in that portion. It's going to stick to this asymptote vertically, so it's doing something like that. Okay? Does that make sense? You guys good with this? Okay, I think you just need to practice. So what I'm going to do, because I didn't get the assignment up for 7th period in time, I'm going to give you guys today and tomorrow to work on this assignment. It's a little bit longer assignment. There's a lot of graphing involved. So give me a second and that'll show up, and then you can start working and getting questions answered.